now. So today we will talk about the plate and shell elements and a brief design of the reinforced concrete slabs and beams according to Australian standard AS 3600. So the plate and shell elements are the plate bending elements is used to model plate type structures where we know that the thickness is very small compared to the length and width, and the loads are subjected to the structure normal to its surface. So we have a plate, thickness is small compared to the other dimension, and the loads are applied vertically on the top of the surface or normal to the surface. So the flexure stresses are dominating in the case. Okay. So, and also we need to know that the similarity of a dimension straight beam model and the 2D flat plate model. So there is some similarities between straight beam and flat plate model. So we can sometimes, in some cases, model the plate as a 1D straight beam elements, as explained earlier in the course. Examples of plate and shell elements are floor slabs, bridge decks, rectangular water tanks, the walls of the rectangular water tanks, and any other retaining structure like tank silos and any other sort of structures. This is the forces and moment acting on a plate element. As you can see, these walls are side of the wall, and you can see this is some pressure on the floor or the top roof. Okay, so the stresses we have is sigma x normal stress, sigma y normal stress, tau xy, and tau zx, and tau yz. So this is the source of stresses we can have in a shell element or a plate element, which is normal stresses and shear stresses. You can see here as well. So we have MOI. This is the applied forces, and here to the left is the stresses. So here is the moment and forces we can have. We can have mxy, and here is mx, here is my. So we have my and mx and mxy, and we have here qy, and we have here qz. So we can have shear forces and moments applied on the plate or shell elements. This is the relation between the forces and the stresses. Here you can see that the bending moment per unit length on a plate is the integration from negative T2 to positive T2, where T is the thickness, sigma x times Z dz. And my similarly, but for the integration is for sigma y, not for sigma x. Okay. This relation how the stresses change in the Z direction. The twisting moment is mxy, or the torsion moment mxy is the integration of tau xy. Instead of integration of normal stresses, it is the shear stress. So the torsion moment mxy, or the twisting moment, is integration of tau xy times z dz. For the shear forces, qx will be tau, the integration of tau xz dz. As you can see here, the shear force is the integration of the shear stress. For the moment, it is integration of the shear stress times the coordinate z, or the depth. For qy will be tau yz dz, tau yz dz. Okay, the maximum bending stresses on a plate element will be positive or negative, means one side is tension, one side is compression. 6 times mx over t squared, and sigma y max is also, we have extreme value in tension, extreme value in compression, 6 my divided by t squared. Maximum stresses is always at the extreme fiber at the extreme fiber on the top at positive t divided by 2, and extreme fiber in compression at the bottom negative t over 2. No middle, no bending stresses at mid surface, similar to the beam model, because this is the neutral axis, so the stresses are 0 at the middle surface of the plate. Okay, this is the finite element for the plate. How can we explain this in finite element? The plate is a thin solid and might be modeled by 3D solid elements. So in the finite element modeling or the software, we can model the plate element as 3D element, but a solid element or a 3D element is a waste of degrees of freedom. So we can model it, but it will waste our time, like, because it need more time to compute. So because the transfers normal stresses and transfer shear stresses need to be computed by the software, which is not needed or almost zero, so it can be neglected. So that's why the plate element will not be modeled as a 3D element, because this is not the best option. So in most cases, we will model it as a plate, like the option in the software as a plate, not a 3D element, because this model considered uh, considered that the negligible stresses which is needed as the transverse normal stresses and transverse shear stresses are 0, so no need to compute it. Okay, in most cases, as you can see, we can draw the plate element with a t, like as you can see here, the t as 0, but this not mean that the plate has 0 thickness. This is just indication that the thickness is already small, and in the modeling we will define the thickness. Okay, so here in this figure you can see that this is the actual plate element in figure A. Okay, and we can show it like this in figure B. So as you can see, the thickness looks like 0, but it has a thickness of t. Okay, so we have 4 nodes for a plate and a thickness t. Okay, and here this is the plate element. This is like the function, the end function for the plate, or how the deformation of the plate is calculated. So as you can see, the plate element normally has 3 degrees of freedom per node, which are lateral deflection and rotation about x and rotation about y axis. Okay, so in any plate element, if you go back, so this plate element we have, as you can see, w and theta x and theta y. Theta x and theta y are rotational deformation. W is lateral deformation. Okay, so as you can see here in this figure, theta x, theta y, w. Theta x and theta y also has relation with w, which is partial deviation of dy. Sorry, dw. So theta y is the partial differentiation of dw over dx, theta x is the partial differentiation of dw over dy. Okay, so for each node in the plate, we have 3 deformation. So for the whole plate element, as we have 4 nodes, so we have 3 times 4, so we will have 12 degrees of freedom per plate element. Okay, the displacement function of this plate element will be something like this, which is W equal to beta 1 plus beta 2x, beta 3y, and so on, and up to beta 12x y cube. Okay, so this is how we can calculate W. And now, after we explain the plate element, we jump to the shell element. The shell element is a thin structure which is bent over curved surface. So shell can be a better representative for the curved surfaces, as in example of curved structure as seed shell or eggshell, containers, pipes, circular tanks, and car bodies, any curvature, roofs, buildings, domes, and any concrete shell structure. Okay, the forces in the shells are membrane forces and bending moments. So we have, like, as you can see, we have membrane force, which is forces in the blade direction, and also bending moment on the edges. So we have bending moments and membrane forces in the shell element. Okay, a thin shell element can be very strong if membrane action dominates. So what makes the shell element strong is the membrane forces, because this membrane force give more stiffness to the element, so it can resist the bending moment. Okay, so the shell element has membrane action, but and also small bending stresses, or little amount of bending stresses. This has some example of the cylindrical container. As you can see, the pressure is perpendicular to the surface. So all of them, we have a perpendicular, uh, a perpendicular pressure on the surface. If we cut here, you can see here in the picture, bottom image, that we have the internal forces like this. So the internal forces will be like tensile forces in the shell itself, or this is our membrane forces. And also here, if you cut here anywhere, so you will have like membrane forces or membrane stresses in the shell element. Okay, this is the degrees of freedom at each node of the shell element. As you can see here, the shell element is a mix or a combination of plane stress element, which has only membrane forces, and a blade bending element, which has like shear stresses and moments. So the combination give us the flat shell element, which has membrane forces and bending moment. Okay, so the shell element is a combination of plane stress and plate bending element. This is the degrees of freedom at each node. As you can see, we have at each node, we have 2 rotational deformation, theta x and theta y, and also 3 deformation, 3 translation deformation, which are u and v and w. So at each node, we have 5 degrees of freedom. Okay, we can have Q4 or Q8 shell elements. Q4, 4 nodes. Q8, as mentioned as in the figure here, 1, 2, 3, 4, up to 8 nodes. Okay, so here for the curved shell element as well, we have 5 degrees of freedom, U, V, W, theta x, theta y, but we will have one more, which is theta z. So the difference between the flat shell element and curved shell element that we have here 5 in plate in flat shell and 6 in the curved shell. Okay, so this curved shell element are based on shell series. Most general shell elements and most general shell element, flat shells and flat element are subsets, and most of them are complicated in formulation. So because they are has curvature, so they are very complicated to model or formulate. Okay, so this was a brief discussion about the plate and shell elements, and we have already done this before. So now, well, from here we are going to like go through the reinforced concrete RC slab design. This is according to the Australian standard AS 3600. So as you can see, we have a floor slab which has like 4 columns in this direction, 3 columns in this direction, and we are trying to design a strip of this slab. This strip, the span of this strip is 5,000, 7,000, 6,000 millimeter. And how much is the width of this strip? Okay, the width of this strip is half of this span and half of this span. But this half and half of span will be increased by 15% from each side. So that's why the strip width will be 1.15 times 2,500, and the other side will be 1.15 times 2,500. So this what is means. This is this increase is to account for the increase in shear in the first span, and this is recommendation from the Australian standard. Okay, here this typical one-way slab, because here the slab is considered as one-way slab, can be analyzed, or this is general notes. Any one-way slab can be analyzed by 1D beam element or can be modeled as plate element. So both of them are okay to model in Australian standard in finite element modeling, 1D element, 1D beam element, or plate element. Okay, the design bending moment and shear forces could be determined as continuous beam. So you can design the bending moment. This is the manual calculation to determine as continuous beam, but there is some restriction or some condition we need to make sure they are happening. That the ratio of the longer to shorter lengths of two adjacent span doesn't exceed 1.2. The loads are uniformly distributed. The life load doesn't exceed twice of the dead load. All these conditions are in the Australian standards. Members are uniform cross section. So the section or the cross section of the whole beam or the whole slab strip are same cross section. The bending moment at the supports are only by the loads, not from the columns. Okay. As you know, here at the connection between the beam and column and slab, there is some moment transfer between the column and the beam and slab. We are neglecting this moment, or if this moment exists, we cannot use this model or this method to calculate the moment and shear forces. Okay, so to calculate the moment and shear forces like a beam, so we need to have this condition applied. Okay, so this is the first part of our slab design or reinforced concrete slab design, that we have load estimation for strength calculation. So we have load estimation for strength calculation and load estimation for deflection or surfaceability calculation. As you know, we have two methods of design. One is the strength design or ultimate limit state design, and the other discipline is the serviceability limit state design. So the first part is the ultimate limit state design or strength calculation. So as we mentioned that we have 15% increase in the shear span in the end span means that in turn of the loading from slab is increased by 1.15. Okay, so that means that the strip width will be 15% from left, 15% from right. So the total width will be 5,750. Okay, because again here this is our 15% from here, 15% from here, just to account for that we have at the internal support here increase in the reaction going to this support. So that's why the Australian standard or the standard recommend to add this 15% from each side. Okay. So if we go to the Australian standard, section 610, clause number 22 and 23, you will find that you need to account for the shear increase by this 15% and 15%. Okay. And also, you can find that this is the moment on the continuous beam or continuous slab strip from the Australian standard. So as you can see, that the moment at the first, the moment here is, just a second, maybe I can explain to you using, okay. Okay, so now it works. Okay, so for the bending moment on continuous slab strip or beam strip, so we have three bays like this. So you expect that we have calculated the loads W, which is W star. Okay, so W star will be the load, or the, you know that we have load combination. So load combination for strength. Okay, so if we know W and we have Ln, whatever Ln, Ln1, Ln2, Ln3. So what is the moment shape you expect? This will be the moment. So we have negative moment at the supports and positive moment in the middle here. The standard give us that all of them will be W star Ln square. So the value that so all of them will be factors of this value. Here the factor will be 1 over 16. Here the value will be 1 over 11. Here the value is 1 over 10 from left, 1 over 10 from right. Here is 1 over 16. Here is 1 over 10, 1 over 10 from left and right. Here 1, 11, and here is 1, 16. So here the moment is W star Ln square over 16, and so on. So this is the moment shape for the continuous slab strip. So if you know the W star from your calculation, you can get the moment at each section. Okay, this is what is meant by this figure. And now, after we get the moments, we will jump to another theory to understand why the reaction are increased in the first support. So now I will stop sharing here. So now if we turn back to the slide, this is the first interior support theory, which indicate why we increase the width of the strip from both sides by 15%. The general case is the simply supported beams or slab. So for simply supported beam, this is how the reactions are, and this is the shear force diagram. So if you have an example, W is 3.75 kilonewton per meter, the reaction in both supports will be 1.5 WL, where W is the load, L is the span. So the reaction will be 13.125. So this will be the shear force diagram. And the loads are equally distributed between two supports. This is the general simply supported simply supported beam. But what happens if we have a continuous beam or continuous slab? If you look here, it's the same beam but two spans. So we have two 7-meter spans. As you can see here, from the shear force diagram from any software, you will find that the first reaction is 9.84. The second reaction is 38.81. The third reaction or the support reaction on the right will be 9.84. And the shear force diagram will be 9.84 up, go down up to 16.41, go up 16.41, and then 9.84. Okay, as you can see here, there is more reaction go to the interior support, and this is what's called first interior support theory. This means that when you apply load on on a continuous beam like this one, so the internal support here has much load or much reaction more than the other supports, which is reasonably because it carry from both sides. But also you can see that it take more than half from left and half from right. Okay, this is what is meant by the first interior support, and this is why we add more like widths, strip widths. If we get a strip width here, so you need to take more than half of this 7 meter and half of this 7 meter. And the standard recommend to take 15% more from here and 15% more from here. Okay, this reactions or this because it is continuous beam, so it is not like a determinate structure, so you need to find the reactions or the shear diagram using a strand 7 or any other software or any approximate analysis you get in your structural analysis courses. Okay, now after we finish the load estimation of for strengths, we jump to the load estimation for deflection. Okay, as you know, the deflection or the surfactability calculation account for the cracking and consequent local reduction of on I. As you know, when you apply load on concrete structure, they start to crack. So the effective I or the effective inertia is not the gross inertia because it has crack. So this will reduce the inertia. Okay, this average or this I effective can be calculated using the Australian standard clause number 8.5.3. And also we need to account for the creep load by by you considering the load, the notional load. This account for creep, which is called FDEF. So notional load is F deflection effective, where sustained load are factored up. So we have two consideration in the load estimation for deflection: I effective and FDF. I effective considering the cracking in the cross section, and FDF is considering the creep, which is significant, uh, significant, like has significant effect on the concrete structure. Okay, so if you go to the general equation of deflection, which is delta equal to 5 over 384 times F times L EF to the power 4 divided by EC times I effective. This is the general formula for deflection calculation for uniform load. But this formula, considering the factored notional load FDF and also the effective inertia I effective. Okay, but in the Stern standard, it is written in a different way. If we consider K2 is a constant, 5 over 384, I effective is equal to K1 times B d to the power 3. So the equation or the formula for deflection can be written as L effective over D equal to K1 times delta over L effective times BEC of divided by K2 times FD effective all to the power 1 2 over 3. This is how the formula is written in the Australian Standard clause number 8.54. It is similar to this one, but considering we replace this with K2 and replace I effective with K1 over K1 BD to the power 3. Okay? And as you know, EC is the Young's modulus or the elasticity modulus for concrete. Okay? In the Australian standard, K2 for different continuity conditions apply. So K2 is not all the time 5.384 because 5.384 is only for simple beam. But if you have a continuous beam, so this factor will be changed by the standard 2.4 times over 384 for end span and 1.5 over 384 for internal span. Okay, so for end span, for continuous beam end span, the deflection is 2.4 over 384. For internal span, it will be 1.5 over 384. Okay. And the values for K1 is K1 equal to 0.02 plus 2.5 rho. Please, can you make this rho? Where rho is reinforcement ratio. So K1 has a relation with the reinforcement ratio of the concrete structure. So 0.02 plus 2.5 rho, where rho is the reinforcement ratio equal to area of steel over B times D. B is the actual beam width, and D is the actual beam height minus 50. As you know from concrete design, B is the beam width, D is T, the total depth of the cross section, minus 50. 50 account for steel cover. Okay? Area steel is equal to approximately M star over 0.7 FSY times D, where M star could be calculated from the moment diagram we did earlier, and FSY is yielding stress of steel, which is about 500 MPa, for example. Okay, so area steel is given by this formula. Then you can get rho, then you can get K1. Okay, so if you need K1 here and K2 and the value of F, value of L effective, and D, so you can get the deformation delta. Okay, and the K2 can be 5.384 if it is simple, 2.4 for end span continuous beam, 1.5 for internal span continuous beam. Okay, so now if we compare I effective with I, where there is no, when there was no cracking, which one will be bigger? I will be bigger, but this is not accurate because I doesn't consider any cracking of the cross section. Okay, so I effective is the accurate method to calculate the deflection for concrete structure because it accounts for cracking. Okay, in this slide, we have to get the F deflection. So when determining I effective, this is also an example for column. When if we are calculating I effective for a column, so it will be taken as area steel 1.01 area gross. In general, I effective for beam is 0.4 times B, while I effective for column 0.8 times BD cube over 12. So if we consider beam only, so I effective for beam is 0.4. Here, this is I effect I without considering the cracking. So I cracking or I effective here is 0.4. So it is reduced by 60%. So that's why I effective need to be considered when calculating the deflection of concrete structure. Okay. There is a formula to find F deflection total, which is 1 plus KCS times G plus epsi S plus KS plus KCS epsi L times Q, where G dead load, Q is life load from the Australian standard. And F deflection incremental, if you add after the addition of the brittle partitions, is F deflection total minus G, where G is the dead load. Okay, so this is the formula for F deflection total to calculate the deformation or the deflection. Assume that psi S is 0.7, psi L is 0.4, from the Australian standard 1117.0. So here we can replace this with zero point 0.7, replace this with zero point 0.4. So if we know KCS, so we can calculate FD total. Okay. So what is KCS? KCS has also a formula equal to 2 minus 1.2 ASC over ASCT, and should be greater than or equal zero point 0.8 according to clause 8.5.3.2, where ASC is the area of steel. Area SC means area steel in compression. So area of steel in the compressive zone of the cracked section between the neutral axis and the extreme compressive fiber. Okay. So area SC is the steel in the compressive zone of the cracked section, where area ST is the area of steel in the tension zone, because area ST is the tension zone. So area ST is the area of steel in the tension zone or in the cross section. Because when we design a concrete structure, we design steel for the tension zone. Okay, so we can assume according to Australian standard clause 8.1, we can consider or assume that area SC over area ST as 0.25. Okay, so if we know area SC over area ST is 0.25, now we can get KCS. After KCS, we substitute here, so we can get FD total. So if we know FD total and we know the I effective, so we can calculate the deflection. Okay, and this is a screenshot from the strand 7 showing the model, a model of a beam or a plate, slab, and this is the columns. The columns height is 360, 3600, 3600, and uh, the supports of the columns are fully rigid from top and bottom. Okay, but this is we just have a look on this screenshot, and we can if you look at the tutorial or the practical materials, you can find an example of the modeling of the plate or the beam, continuous beams. So please try this, and you can find something like this in your model. Okay, I think it is example 4. So if you go to example 4 and 5, it is considering uh, not example 4 and 5 in the, I mean, the tutorial, the practical number 4 and the practical number 5, which is modeling a continuous beam and a whole concrete slab structure. Okay, I will try to give you some tips about this. Okay, now if we go to this example, this example is a simple example of finite element modeling of 2D plate elements. If we have a simple slab with two beams, the span of slab is 5,000 millimeter between the two beams, and the length in the other direction is 3,000. So we have a slab of 5,000 times 3,000. Thickness of plate is 200 millimeter, and we have a concentrated load applied at this point to one of the sides. Okay, and here is like a mesh, of the slab, an example of meshing of the plate, and we have here one support to the left, one support to the right, and one support to the left. The support to the right is roller here. Support to the left here is hinge. Okay, so now if we draw this on the on the strand 7, model this on strand 7. So we will have a plate element, and we have this side to consider it as hinge, and we this side consider it as roller. Okay, so as you know, roller means that prevent the movement in z direction, but allow the movement in x direction or y and x direction. Here, because it is a plate, so we have three axes. We have x in this direction, y in this direction, and z. So we have x, y, and z. So as you can see here, we have x, y, and z. Okay, so just a second here. If we go back to here, so we have, if this our plate, so we have three axes: x in this direction, y in this direction, and z direction. Okay, so this is our axis. Okay, and this side we have ruler, and this side we have hinge. That's why in the finite element model or in strand 7, here on this side, we will just restrain if we have a mesh or subdivision like this. So we have some nodes to the left here, to the right here, sorry. So what we will do is just prevent the movement in Z. So Z is restrained, but we allow X movement and Y movement. Okay, but what will happen in the other direction, in the other side here, this nodes? Okay, also because it is hinge, so we have to prevent Z anyway, and but if we prevent Z only, so it is allowed to move in X or Y. So what we will do is just prevent the movement in X and Y and Z for these two nodes. For the nodes on the edges, these two nodes, we will prevent X and Y and Z. And for the middle ones, we will prevent only Z. Why is this? Because the support here under the beam, under the slab, as you know here, we have a beam. This beam will be allowed also to deflect. Okay? Or allowed to, there is no support to move to prevent it from going left and right in the middle here. So that's why we need only to prevent the movement in all direction for this two and allow X and Y for the middle one and prevent only Z. So for the middle nodes, we prevent Z only, and for the edge nodes, we prevent X and Y and Z. But for this side, because it is a roller, so we don't need to prevent X and Y, and we need only to prevent Z. Okay, so now if we go back to our slides. Okay, so this is how to show the stresses in the strand 7. So if you want to show the stress for this plate, So you need to click the this maybe I just show you as well on the strand 7 itself. Okay, can you see strand 7 now? So okay, thank you. So now on strand 7, if we have a blade, I will create only first nodes. So create node to draw something like this. We need to create node. So we have node 4, node 1, and node 2 will be 0, y, and an x will be 5 meter. And we have node 3 is 5 meter x, 3 meter and y. And we have is 1, 0 and x, 3 and y. So we have 4 nodes. And we will create element between these nodes, which will be quad 4. So if we have quad 4 element, so this is our blade element. And now if we subdivide this, so from tools, subdivide, this is our blade. So I will make it 100, so it will be 50 and by 30. So 100, and I will make it quad 8. It's too much, so maybe make it uh, half. So 25 by 15, quad 8. So apply. So now this is our plate element. Whatever the subdivision you want, you can do it. Doesn't matter. So now second is attributes node restraint, as I told you here. If we pick this side, this is the nodes on this side. So we will only prevent the deformation in Z direction, apply. And for this side, sorry. Okay, so this is the blade. As you can see here, we prevent only in Z direction. If we go back to view, XY plan, so this is our plan. So I will select this nodes, attributes, nodes, restraint. So select this nodes And these nodes, we cannot select them all, so clear selection. So we will select only the nodes in the middle. From here to here. These nodes are only Z direction, so apply. And I will select this node, the nodes on the edge here, this node and this node, and prevent X, Y, and Z, apply. Okay. As you can see here, if we click the view, angles, diametric, apply. So you can see now the the restraints, and go back to view, angles, XY plan. So now we have modeled and subdivide the plate element. And as you know that we have a load here on the in the middle. So I will define the load, but before the load I will define the plate. So we have a plate element here. This plate is plate element, or what is the type of plate? Plate, because it is a slab, so we mentioned that we are using the plate element. What is the material? So we will go to the material. As you know, the material, we know you have a lot of materials here. So we have concrete, AS3 600. So whatever the material you want, we can use depending on the problem. So we can take this 32 megapascal. Okay. So the material here is concrete 32. And the geometry, we need to define the membrane thickness. What is the membrane thickness here? It was 200 millimeter. So it will be 2.2 meter. So now if we have a view, diametric, and view at intensity display. So for the plate, we know show solid, apply. So now as you can see, this is the plate element after we give it the thickness. So everything is now ready. Now we can return back to our 2D view, XY plane, and intensity display, we make it surface again, apply. And now where is the load? The load was in the middle here, in the middle span here. So if we can 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so it will be here. So this is our middle. Okay, so need to tools or attribute, sorry, node force, because this is a node force and the force is in Z direction. How much the load was? The load was 100 kilonewton. So, and it is going downward, so -1. So we need to select a node. So the node is here. Let's say it is here, apply. If we have a view, as you can see, now is the load is like this. So we have the load applied and everything is okay. And now, as you can see, the load here is point load. So the load here will cause some stress concentration at this area. So what we need to do, sometimes we need to If we go back to the lecture again, sorry, just a second to show you. Before showing the result here, okay, as you can see here, there is some explanation about the stress concentration in this node. So what we can do is make a fine mesh around the node. So when you have a fine mesh, so this will make it more correct or more accurate. Okay. So what we can do is divide this mesh around here. Let's say this four blades around the load here, as you can see, this area around the load. We can divide it by uh, subdivide. So we can subdivide, and then the problem will be the elements around. So if we go back to the problem, the software, what this means that we can go to tools. First, I will make zoom here. This is the area we are talking about around the load here. So we can subdivide tools, subdivide these two, let's say, element. As you can see, we have subdivide this area. But the problem now will be that the mesh in this elements need to be fixed because this mesh, this six plates are connected from here with the plates is the original size of the plate, but from inside they are connected to the small side. So we need to make like in like transition zone. So these six elements need to be cut or subdivided with a different method. So how can we do that? What we will do is pick this edges and firstly go to tools. You remember last week we did the grade blades. You remember this one? And we will select this option. So this option will make it like big from one edge and divide it by two in the other side. So if I select these elements, these edges, sorry, and let's see what will happen and apply. Okay. So what you can see here, if I zoom, maybe I need to, as you can see, can you see the screen clearly? That might be not easy to see, but anyway, try to find something to make it easier. Maybe make the plate. Yeah, okay, there it will be better. Now, if you look at the this part here, what I have done here is around the point load, I have make a fine mesh, which is means smaller size of mesh. But here the problem where in this plates, because these plates are connected from the side with a bigger size and from the side with a smaller size. So using the grade and cut edge, we make it from the side matching with the mesh here and from the side matching with the mesh here. Similarly in this element and similarly in this element. Okay. So this is what is meant by we are making a fine mesh around the point load. Okay, I think now we are ready to run the model. So from solver, linear static. Sorry, it appeared in the other screen. So linear static, let's say this is plate number one and solve. Okay, and here the run is finished, no errors. So open the result file, open, and here we can show the displacement scale. Okay, let's say 10%, apply, and view. And here is the plate. As you can see, this is the deformed shape of the plate. And if we want to show the result, so as contour, if you want to show the deformation, so displacement, what is the direction of the deformation here? DZ. So apply DZ. As you can see, this is the contour view and XY plane. So this is how it is the deformation of the blade. As you can see, the maximum deformation is negative 7.11 times 10 to the power negative 3 in meter, which means 7.11 millimeter. So the maximum deformation will be under the load here, which is negative 7 millimeter. If you want to show the stresses, so result settings, instead of displacement, we can get stresses. We have different component of stresses and different axis systems. We have local, global, USC combined. So we have XX combined and so on. So just leave this now and I go back to the slides because we want to show you what is written in the slides first. So now after we solve the example, this is this slide explain how to read the result or how to get the result from the software. So click in the top menu, rainbow, result setting icon, stress, axis global, XX, what you will find. You need to select positive Z or negative Z. Okay, so this means that if we go back to the software, so if you look here on the top, you see this rainbow colors. If we click it, so it is open same as from here, from this list, result settings. Okay. So from result settings, sorry, now you see the software. So what is mentioned in the slide, result settings, access system, global. So under stress, if you want to show the stress, under system, global. So you have different component of the global system, X, X, Y, Y, Z, Z. If you want to show the stresses in X direction, sigma XX, we have middle. So the surface is middle, positive Z, and the negative Z. What this mean? This middle means the middle of the thickness if we apply. So there is no stresses in the middle. As we mentioned earlier, that there is no stresses in the middle because it is zero. So we need to select negative Z. So this is the stresses at the bottom, negative T by 2. So this is the stresses from the bottom. And if you select the positive Z, this is the stresses on top. So you need to know what stresses you are showing and what is required to show. So to show the stresses in X, global, positive Z. If you want to show in Y direction, similarly, we have this is the stresses in Y direction, which is perpendicular to X direction. So we have also positive Z, negative Z, and so on. We have also tau xy or the stress xy. If we apply, this is the shear stress tau xy at negative z. This is stress positive z, and this is stress in the middle. So as you can see, there is nothing in the middle, and we have yz. As you can see, we don't have the component yz because we mentioned earlier also that there is no shear in yz. So what we have in the plate element, we have sigma xx, sigma yy, tau xy. This is the three important or the three available stresses in this type of structure. Okay? Do you understand this plate example? So again, if we show here, and also the second, if we go back to the slide, after we know how to show the stresses. So to investigate the variation of stresses, you can use the peak option and click the plate icon stresses, global, XX, negative Z, and then click the plate on the listing. So if we do that, we go back here. So we have, this is the peak option. You see this microscope on top. This is the big option. So this is a big option. So you can select a certain plate or a certain value. So if we go to stress, global, XX, you can hide all of them, and negative Z, and select this stress. Or firstly, I will show the stress. So stress sigma XX, negative Z, apply. So this is the stress. If we want to get the stress exactly at one plate or one point, so from peak, select the plate. We already we can select this plate, global, sigma XX, negative Z. So this is the points, the edge, as you can see, if we can zoom. As you can see, we have, this is the points. It's called GB. GB means Gauss point. This is the point where the stresses is calculated by the software, not the point to the edge. So the software calculates the average stress at this 3 point, Gauss point 1, Gauss point 2, up to 4, and this is the value of stress at this point. Okay? So now we find the stresses and know how to show the stresses. And we know that we have tau xy and sigma xx and sigma yy. Okay, and now we finish this example. Okay, and you know how to do it. But if we go back to the slides, the last slide in this lecture is how to print the strand 7 results. Okay, you have a different option, and you need to, because you need to show this in your report. So you have some options. You have control print screen. Okay, so if you want to copy the entire screen without any overlaying window, so you can use control print screen and then crop or cut and edit and copy to your report. The other option is alt print screen that only copies the active window and is useful if you have overlying windows. So it will only print the active window or active window of strand 7. Finally, and generally most usefully from strand 7 top menu, item edit, select copy graphics. So this will copy just the graphic model without the borders, and then control V or paste and paste your image in the Word document. So if you go back to the strand 7 again, you have edit here on top. You have copy graphics or shift control C, and then you copy this and then paste in your Word documents. Okay. So you have several options to copy and paste your your graphic or your model in your report. Okay. So now we'll have the next lecture will be lecture number 6, 3D problems and element selection. Okay. But I will just have rest for 5 minutes and then we can continue. Okay. Thank you. So again, guys, if you didn't hear me, we will have a rest for 5 minutes and then continue our lecture. Thank you. ，Hello guys, how are you? I'm back. Sorry for being late. So now we will go for the material lecture 6, which is the 3D problems and element selection. So in the previous lecture 5, we talked about the plate and shell elements. In this lecture, we will be talking about the 3D elements or 3D problems and how to select the best element type. Okay. The solid elements, or known as the 3D brick elements, are used to model structures in which the thickness is substantial when compared to the other dimension. So here, the thickness is, we have bigger thicknesses, not thin thicknesses like in plate or shell elements, and the thicknesses has substantial effect on the behavior. So that's why the structure need to be modeled as 3D or solid elements. Examples of these solid elements are valve and gear housing, bearing races, thick welded joints, and thick walled cylinders. Okay. For solid elements, all 6 possible stresses are valid and need to be determined. So we have three normal stresses and three shear stresses. So we have 6 possible stresses valid in this type of element. Okay. By using the number of brick elements through the thickness of the part, the stress distribution can be accurately obtained. So if the structure is meshed properly, so this means that we can find the stress distribution over the part or over the structure. This is the main idea about the solid elements. Okay, as example of solid element is this example here is this cube or this rectangular faces shape. We have 3 dimension or 3 direction, sorry, X, Y, Z. And as you can see, each solid element has 8 nodes at least. Okay. So a 3D brick element normally has 8 nodes. So this is the normal shape or the regular shape. Each of them has 3 translations. So 3 degrees of freedom, X and Y and Z translation, X movement in X, movement in Y, movement in Z. However, some programs or some softwares support variable node break elements, which can support as many as 21 nodes, where high degrees of accuracy is required. Okay, so in strand 7, we can model the 3D elements by 8 nodes, but some softwares can reach up to 21 nodes if you need more accuracy for the results. Okay, if you can see the figure here in the bottom, this show an example of a complicated solid element. So this can be if more accuracy is needed. So the solid element can be up to 21 nodes. Okay, problems of beam bending or plane stress or blades or any other problem type we studied before or we explained before earlier in the course can be regarded as special case of a 3D solid element. Okay, so any problem can be 3D solid element because this is the actual structure shape because any structure is a 3D element. But we prefer to model this type of element like beam bending or plane stress or blades or shells and so on because this will save computational time or save our effort to solve because you have some simplification and give you some good like accurate results. So you don't need to go for 3D elements because the 3D elements or 3D models are hard to prepare and the most tedious to check for errors and most demanding in computer resources. So it is very complicated to model the 3D structure model. So that's why if you have another option or a simplified option, it's better to use to save efforts. Okay. This is a typical type of 3D elements which can be used in any finite element software or any finite element analysis. We have tetrahedron, which can be linear or quadratic. So tetrahedron can be 4 nodes, like 3 on the base and 1 on the crest. 4 nodes or 10 nodes. As you can see, each element has 3 nodes, so all will be 10 nodes. Okay. The tetrahedron linear elements should be avoided in 3D structure analysis because it is inaccurate. It is only accurate for the dynamic analysis. So if you are doing any static analysis or any 3D modeling for like normal loading cases, don't use tetrahedron. The second one is penta, okay, which is like triangle and on the top, triangle and the bottom, and connected with rectangulars. So we have two types of penta, like 6 node, which is linear element, or quadratic element with 15 node. So again, linear means each line or each side has node at the beginning, node at the end, but no nodes in the middle. But for the quadratic, each side is divided by a node in the middle. Okay, the last one is hexahedron or the break element, which is a common one to use, which has at least 8 nodes for the linear element or 20 nodes for the quadratic element. So this is the major types of the 3D elements: tetrahedron, penta, and hexahedron. All of them has linear and quadratic element. So this is the typical 3D elements used in finite element. Now this is the stress-strain relations for a 3D model. As you can see here, this is a stresses vector, which contain all the possible stresses as we mentioned: sigma x, sigma y, sigma z. So the 3 normal stresses: tau xy, tau yz, tau zx, which are shear stresses. This stress is equal to E triangle modulus over 1 plus nu, which is Poisson ratio, the times 1 minus 2 times Poisson ratio, multiplied by this 6 by 6 matrix, which has like most are zeros except for the diagonal and these three elements here, new, and the diagonal is 1 minus new, 1 minus new, 1 minus new, 1 minus 2 new over 2, 1 minus 2 new over 2, 1 minus 2 new over 2. Okay? Here is the times the strain vector. The strain vector is epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. Okay? Or in a simplified uh, formula, sigma equal to E times epsilon, where this is sigma, this is the vector sigma, this one, this is the vector of epsilon, the strain, and all of this, sorry, all of this from here to here, like E over the two brackets, and all this matrix is E. Okay? So this is the stress strain relationship for the 3D element. And to get this, we need to know that the displacement U within an element are interpolated from the nodal degrees of freedom D in the usual way, similar to other elements we studied before, that you need to find the displacement U in the middle or at certain point of the element using the degrees of freedom at the nodal or the nodal displacement at the nodes on the edges. Okay, so like here, to know the U in the middle here, you need to know the displacement at the four nodes. So U equal to ND, where N is the shape function matrix, and nodes have only translational, and N is the number of nodes. So as you know, each node has three transitional displacement or degrees of freedom, and N, depending on the type of element, hexahedron or tetrahedron or penta. So that's why N has 3 N columns for a 3D element. So the shift function has 3 because each node has 3, and N is the number of nodes. So if you have 8 nodes, so N has 24 columns, which is complicated, so much complicated. Okay, so as you can see here, this is a displacement field, as we mentioned, U, V, W, displacement X, displacement Y, displacement in Z, equal to this matrix, 3 times 3N. So depending on how much N, how many N, times U1, U, V1, W1, U2, V2, W2, up to 3N. So if you have 8 nodes, so 24. If you have 8 nodes, so this will be 24. So it is much complicated. Okay. A general formula is U equal to N times D. The strain vector is, as usual, epsilon equal to B times D. So if epsilon 6 by 1, B is 6 by 3N, and D is 3N by 1. So the final product, whatever the nodes are, the number of nodes are, will be 6 by 1. The stiffness matrix, also similar to the previous. So all this is similar to the previous elements we studied before, just the size of the matrix is different. So the size of the matrix depends on how many nodes, but still epsilon equal to B times D. And also K, the stiffness matrix, is the integration of B transpose E, P, dV. Okay, where K will be 3 times N, where N is the number of nodes. So if you have again 8 nodes, this will be 24. So it will be 3 by 8. Sorry. Sorry, this is wrong. So K will be 3n times 3n. So as you can see here, we have 3n. So if you can edit this one, please. This should be 3n times 3n. So the stiffness matrix will be 3n by 3n because we have K is the integration of B transpose, which is 3n times 6, times E, which is 6 by 6, times B, which is 6 by 3n. So the final value or the final product will be 3n times 3n. Okay. Okay, so now this is how the loads are modeled on the 3D elements, and this is note is important again. The 3D elements are only use translational degrees of freedom as before here, U, V, W, and don't use rotational degrees of freedom. So there is no theta x, theta y, theta z in the 3D elements. So the 3D elements are only has three translational deformation at each node and no rotational deformation. Okay, for the loads, if we have distributed loads on the 3D elements, the software cannot understand the uniform load, so we need to convert the distributed load to nodal forces at each node, depend on the number of nodes of each element. So for this element, if the loads are applied to the top face, so we have 1, 2, 3, 4, 5, 6, 7, 8 nodes. Okay. And for the distribution of the nodes, the software the edge node will take B, which is the pressure, times the area of the face divided by 3. So each node will take B times A over 3, and the corner nodes will be B A over 12. So the edge node, which is this node, and this node, and this node, and this node. So this edge node, this is the edge node here, will take BA over 3. So this is for each node, BA over 3. Here, okay, the edge node, the corner node will take BA over 12. So corner nodes BA over 12, edge node BA over 3. And as you can see, the edge node are going down and the corner nodes are going up. So the load will be converted from uniform load to to edge to nodal forces like this. So the nodal forces on the edge or in the corner, will be going up as a reactions, and the edge nodes will be going down similar to the loads. The summation, if you sum all together, so we have 4 corner going up, so 4 times B over BA over 12 will be BA over 3, and the edge node are BA over 3 times 4 going down, so the sum of all together will be B times A, which is the pressure over the surface. Okay, so this is how the load are converted The edge nodes are take the loads down, and the corner node will take the loads up. Okay, this is how the software understands the distributed forces. Okay, this is why we shift, or when we shift from 2D to 3D. As you know, all the real structure are 3 dimension. No structure is 2D, but we use 2D to simplify our model because the 3D structures are, as we mentioned before, like complicated to model, hardest to check, and also take like excessive computational time. The 2D analysis is substantial, dependent on the convention and the approximate associated with stacks with the 2D analysis is substantially dependent on the conventions and approximation associated with extracting 2D models from 3D structures and apportioning loads to the 2D models. Okay, so this means that the analysis of the 3D or the real structure depend on how can we simulate this 3D structure as a 2D structure and how can we apply the load to this 2D model, because in some cases we cannot get accurate results from the 2D model, so we don't have any other option rather than using the 3D model. Okay, the third option is we have many convention approximation in 2D. There are many conventional approximation in 2D and modeling, and this may give rise to significant difference between 3D and 2D results. As I mentioned before, that the 3D model is the most accurate one, but we need to make sure that the 2D model we create is very close or give a close result to the 3D model. If it doesn't give us this, so we cannot use the 2D model. Okay, to overcome the problem of modeling the 3D problems, we can use 2D drawings. Oh, sorry, we can use the CAD drawings, 3D or 2D, to model it on strand 7. So, like importing the drawing to strand 7. So, how to convert CAD geometry file to strand 7? The model, the CAD model, if it is saved as IGES type, so it can be modeled or imported to strand 7. Okay, so there is option to import strand 7 from strand 7. But what is the condition? The condition is we need to make sure that the file is IGES format or extension. Then after we import the model or the drawing to strand 7, the model can be auto meshed. We have two types of auto mesh or two procedure for auto mesh. We will know later. You can assign attributes such as boundary condition and load to the model. So after you auto mesh the model from AutoCAD, you can apply the loads and boundary condition and so on, similar to any other model we did before. Yeah, under the model auto mesh, there is, as I told you, there is two types of meshing: surface auto mesh or solid auto mesh. We will see now what is the difference between them. As you can see, this is an example of a 3D problem. This is a drawing on AutoCAD here on the left here, and this is a solid auto mesh, and this is the surface auto mesh. Solid auto mesh means that the software will auto mesh the whole body as a whole, as a unit. For surface auto mesh, for surface auto mesh, it models surface by surface. Like as you can see, this surface is green, this surface is orange, this surface is light blue. So the software mesh surface by surface, not the whole body together. Okay, and this is the CAD mesh, or this is the mesh after exporting, or after, I'm sorry, importing from CAD. But then you can do the auto mesh here, and or using the solid auto mesh or surface auto mesh. So you have to this two option to model or auto mesh the CAD model. Okay, so this is what was about the 3D element or the 3D modeling. Now we will go to how to select the best type of element. So because we have now finished all the element types from beam element, plane stress, plane strain, and shell and blades and so on, and 3D elements at the end. So when to select the element, and what is the best type to select. So before defining the nodes, it is necessary to determine what type of element is appropriate for the problem. The selection of element will influence the definition of nodes. Because as you know, each structure has its own performance or like behavior. So we need to select the elements depending on the behavior, and this element type will affect the nodes, because as you know, each element type has different deformation in each node. Like as example, today we talked about the 3D element, which has 3D. For 3D, the each node has three translational deformation, U and W and V, U, V, W. So we have deformation in X direction, Y direction, and Z. In other types of elements, like the shell elements, we have like three deformations, three transitional deformations, and three rotational. So like the curved shell. So this what is meant by this statement, that each element type will affect the nodes, because it is it is affecting the degrees of freedom at each node. Okay, and then for structure, consisting of beam and trusses, this is how to select structures that consisting beams or trusses should be modeled with beam or truss element. This is as the first example we did in the practical of the software last week. So if we have a truss or or frame elements, so need to be modeled using beam element. You don't need to model it as 3D. If the program doesn't provide truss element, like any other software, because Trans 7 can model the truss, can be modeled as beam element without moment capacity. So some software doesn't have the option of trusses, so you can overcome this by model it as a beam element without moment capability or moment capacity. So you can define the moment capacity as minimum or almost zero. So the software will understand that this member cannot carry moment, so it will work as a truss element. Okay, so to do this, you can define the inertia of the element as zero. So if the member has no inertia, this means that it will not carry any moment and it will work as a truss. Okay, in general, any object whose length is much greater than its depth or width can be modeled with beam element. This is a general rule. Any structure element, the length is very much greater than its depth. So the depth is very small compared to the length and the width, or the depth or the width, the depth or the width. So you can use the beam element. Okay, so beam element can be used in this condition. Modeling beam element is straightforward as long as the sectional probability are defined and the beam is oriented probably. Okay, this is the simplest element we have, which is the beam element. We have two examples before on this element. This is some examples of truss or beam elements. This is a truss, beam jointed 2D truss. Okay, as you know, you can just draw the members, and when you define the members on strand 7, you can you can select a truss so the software understand that it is a truss. This one is a 2D frame in XY plane, so you can draw also and select a beam instead of truss. This is a 3D truss, fully triangle, fully triangulated. So it is all triangulated. So you can also model it as a beam element, but 3D beam element. This one is a 3D welded beam element. Okay. So this is some example of truss element or beam elements. Now we go to when to select the blade element or break element, because in some cases they are close. So the choice between blade and break elements are not always straightforward, especially in the problem with bending stresses. Okay, because some break elements or some like 3D elements are subjected to bending moments similar to the blade element, like the slab or the slab bay we did earlier this lecture. It was a blade element, but you can also model it as 3D element. In blade elements, there is no variation in stress through the thickness of the blade. So the blade element consider the stress on the blade is has no variation. So the blade element has this condition. This assumption is only valid provided the thickness is much less than the other dimension. So this can be only applied in thin structures. So like slabs. So for beams it doesn't work, or not all the cases will work. So in some cases the blade element doesn't work when the thickness is not very small compared to the other dimension, the width and length. In general, the blade elements are appropriate when the thickness is no more than 10% of the other dimension. So if the thickness is less than 10% of the other dimension, we can consider it as thin element and you can use the blades element, not the 3D element. If the thickness is like more than 10%, you can you have to use the 3D element. Okay? Selection of element type. If your problem doesn't fit the criteria for beam or blade element, the first step is to evaluate the possible simplifying assumption. If we have problem like this, and you can see that the criteria of the beam element and the blade element doesn't work, so we need to evaluate first some simplifying possible assumption before go to the 3D element. Okay. Can you are can you use the 2D element to model this type similar to the figure we have? I think this element cannot be used as 2D model. Do you have any axis symmetry? Is there any symmetry about this, about any axis? I can see if you can see any symmetry, or you can't use the axis symmetry option, similar to the problem we did last week in the plane stress elements. If you have symmetry, you can use it, but if you don't, so there is no option to use it. Okay. If this assumption doesn't apply, so the only option we have is 3D model. Okay. So what is this means in this slide is that if you don't have the beam or plate option, so you can search for other option like the axisymmetry or try to simplify the model to 2D. But if you don't have these two options, so the only option will be 3D elements. Okay. So the general or the summary of this is you need to find the more simplified, the most simplified beam element to use, oh, sorry, the most simplified element to use to model your structure. Otherwise, you will waste your time and waste your effort. So if you have option to use a simplified element like beam element, plate element, plane stress, plane strain, axisymmetry, any other element, so use it before go to the 3D element. But in some cases, there is no option rather than the 3D element. Okay. This is some example of 3D element converted to 2D elements or a comparison like this is actually a 3D, but you can model it as 2D. This also the example we did last week, similar to it. 2D plane stress element, and you can use the axisymmetry because this axis is axisymmetry, and this is also x-axis is symmetry. So you can do a quarter like this. You can do this quarter and model it using 2D plane stress. Here we will do this uh, in a practical, the next practical. So this is also a 3D dam, but you can use it as 2D plane strain element. This is also a mechanical part or like a cylindrical container or something, but it is symmetric. So this x, y-axis is axis of symmetry. So you don't have to like model all the parts. So you can only model half. So if we model this half, this is called X symmetry. Okay. This is 3D plate shell element. So there is no symmetry. There is no option to do it as a beam element or a plate element because it has opening and so on. So you have to model it as 3D plate or shell element. Okay. So you cannot model it as 2D or plane stress or plane strain elements. Okay. Finally, you may require spring or stiffness element to middle support points of the structures. If the stiffness of any part of the structure is known, this part can be modeled with a spring or stiffness element. So if the stiffness of any part of the structure is known, this part can be modeled with a spring or stiffness element. So if you know the stiffness, you can remove the part and use it as because you know actually what is the actual behavior of it, so you can model it as a spring. Okay. If other special elements are required, such as lumped mass, this should be noted in the on the preliminary sketch. Okay, lumped mass is uh, a term used in the dynamic analysis to represent the mass of the structure and represent it in one point. So this is called lumped mass. So this lumped mass need to be defined in the preliminary sketch of the structure before modeling it. Okay, and that's it for this lecture.